inviting me to give this talk. It's a pleasure for me to be here, to be back in Colombia. I don't live here anymore, although I've lived here for many years. And it's really exciting to have all of you young people here in Colombia doing what has fascinated me for so many decades, physics. So my talk today is really about why are we all here? Or how did we come to get here? And it's not so much an existential question, really, although it is a question of that sort. I want to ask this question from the physics perspective. Because the fact of the matter is that all our most fundamental understanding of the basic laws of physics cannot explain why we see an asymmetry of matter over antimatter in the universe. Everywhere we look, we see stars, planets, galaxies, the chairs you're sitting on, the air we breathe, it's all made of matter. And the fundamental question is, why did the universe choose matter? The way we quantify this is by measuring a specific ratio that's called the baryon to photon ratio. And it's that really, really tiny number on this slide, 6 times 10 to the minus 10. That's the ratio of the baryon number to the photon number in the universe. And it's been measured very precisely, and I'll go through a little bit about that. But that number is the reason we're all here. So we can all feel part of a mystery, a fundamental mystery of the universe. And my talk is going to be really at the confluence of particle physics and cosmology, try to show how they play off each other, complement each other. And hopefully you will all learn quite a bit today. So we had at the very early stages of the universe, the Big Bang. And the Big Bang produced this, was followed by inflation. The universe then had an epoch of particle production. But the fact of the matter is that unless, and this is the caveat, there was some initial condition that we don't want to consider at this time that initially separated matter and antimatter with this precise amount, when the particle production occurred, there were equal amounts of matter and antimatter that we produced, the same abundance, right? Now what happens when you have matter and antimatter, if they come close enough together, they will annihilate, they will leave only radiation. And so what we would expect to see in the universe is that, just light maybe, no structure at all. But that's not what we actually observe. We're here, every single one of us. And I want to try to give you a little bit of an intuition and a sense of the physics beyond what would we need to be able to have this excess of matter over antimatter. So let me start with the framework. There's a very strong theoretical framework that has been proven experimentally to high precision. And it really gives us a map of, if you want, the fundamental ingredients of the universe. What are the parts that are, if you want, the catalog of the universe, from which every single planet, galaxy, star, ourselves, etc. is made of. And of course, given that this is a physics Olympiad, I had to write one equation, only one, which is this Lagrangian. Now, one can understand all of physics, really, by variational principles. The principle of least action will give you classical mechanics. It will give you electromagnetism, which you all should know really, really well. This is a Lagrangian from which you can build an action that will give you all of the physics related to the fundamental particles and their interactions. So it's really important to understand that this map gives us all of the things that we know, but it's also very clear in determining what we don't know. So here are the constituents of matter, the particles that make up everything that we know of. And we have 12 fermions that are separated in 6 quarks and 6 leptons. but you only need the two first quarks, U and D, to make up the protons and neutrons, and of course you need the electrons to make up the atoms. And once you have this, you have all of the chemistry, all of the biology, everything you need in the universe. And of course you have additional particles, fermion particles, that are heavier versions of these basic first family, let's say, constituents. In the lepton sector, you also have neutrinos, which are very special because they really don't like to interact with almost anything. And you have trillions of neutrinos passing through us every single second, through Earth, through every single one of us. And they interact very, very rarely. But those very rare interactions can tell us a lot also about the universe. And we have four fundamental force carriers, which we call bosons. So we have the one associated with electromagnetism, which is the photon, which is massless. And then we have the weak force carriers, the W and Z boson, and the gluon, which is related to the strong force. And finally, we have the most recent discovery of the Standard Model, which is the Higgs boson. And I say most recent, it was a mega discovery. Happy to be part of that effort. But it already happened 14 years ago. And the Higgs boson is really special because it's a scalar particle. And it's the only scalar particle that we know of. Fundamental scalar particle that we know of. And it's really, really important because it has, it's the evidence, the Higgs boson itself is the quantum excitation of a background scalar field. And that scalar field is super important because it's what gives mass to the other particles of the Standard Model, including fermions. And I'll go into this in a little bit more detail. So we have these four forces that we have known for a long, long time that really are at the crux of what constitutes the universe. And just to look at a little bit of a comparison of the strength, the relative strength of gravity in comparison with the strong force, you have it's 10 to the minus 39 times weaker. You won't think it's irrelevant, but is it irrelevant? No way. There's no way. All our galaxies, the stars, the planets, ourselves, being able to walk on Earth, it's all due to gravity, right? Then we have electromagnetism. It's 10 to the minus 2 times weaker than the strong force. Super important for, as I said before, being able to have atoms, chemistry, biology, everything. And then the weak nuclear force, which has a very, very short range of strength, which is only 10 to the minus 16 centimeters. Tiny. One would think, ooh, isn't that irrelevant? Wait, no, it's not irrelevant at all. It's fundamental. Fundamental because it is what causes radioactive decay. And without radioactive decay, we wouldn't be able to have our stars burning in the way that they're burning that help life on Earth and so on and so forth. But the key thing that I want to focus on is that very high energies, actually electromagnetism and the weak force, are identical. So there's a unification of these forces if you go to very high energy. Not at the energy scale that we live in. We can distinguish them very well at the energy scale of our daily lives. But at very high energies, they become indistinguishable. And that is a very key feature of the Standard Model. And the way that we understand this is through something that's called electroweak symmetry breaking. Okay? So electroweak symmetry breaking is fundamental. You have the Big Bang, you have the unification of the electromagnetic and weak force. They're identical, and all particles are massless. So the universe is expanding, it's cooling, and as it cools, all of a sudden, the Higgs field switches on. When it switches on, a lot of different things occur. First of all, the particles get mass. Then it breaks the symmetry, and at the same time, it's breaking the symmetry of these two forces. So you have a very, very different universe that evolves after that breaking of that electroweak symmetry. And eventually, the universe will continue to evolve, to cool down, and to be able to generate all the atoms and the chemistry and biology, etc., etc. I want to insist on this because it's extremely important. If electroweak symmetry breaking did not occur, then the weak force carriers would be long-range forces. The electron would not have a mass, If it doesn't have a mass, it cannot couple to an atom. It would be flying away at the speed of light, and we wouldn't be able to have constituents of matter at all. It's extremely important, so fundamental. I wonder how many people back in 2012, when the Higgs boson was discovered, realized, wow, this is really giving us an explanation of why we are able to evolve in the universe to a setting of like what we all see in our daily lives. So it's actually really fascinating, and I want to tell the story of the machine that went to try to find the Higgs boson. I already told you it was found in 2012. But to do this, we had to build a really, really complex instrument. The most complex instrument built by humans, I would say. And it brings in another aspect of science that really is that intersection of science with other fields, with engineers, with a whole bunch of other expertise that's necessary to get these mega projects done. So what is this machine? This is the Large Hadron Collider. So it's a collider that is 100 meters underground, 27 kilometers in circumference. It's located in the border between France and Switzerland. And it's circulating protons at incredible speeds, very, very close to the speed of light. And these are going around at 11,000 lamps per second, these protons. And all of a sudden, we have the two opposite beams, and they collide. They collide at 4 points in this circumference. And we have a frequency of collisions of 4 million collisions per second. That's outstanding. However, that's too much too much for what we can actually register in the data. So we can only keep like 200 per second information of only about 200 per second collisions. We have to really be selective. We have to be selected at a speed that is incredibly fast, much faster than what we can actually appreciate. So we have to be really smart about how to do this. So this is one of these massive endeavors. You know, you're producing this collision, you're trying to recreate that moment of energy very close to the energy of the universe when the electroweak symmetry broke. So keep that in mind. We're talking about 100 times the mass of the proton, 100 G. But it's not enough to have the protons collide. We need to see what comes out of those collisions. We need to understand what are the particles that are coming out of each collision and characterize them. Understand what is their charge, what is their momentum, and we can measure their spin, for example. All these fundamental quantities associated to the particles. And to do this, we need to build these massive detectors. And there are, as I said, 4 major detectors on the ring of the LHC, but I'm going to talk only about one, ATLAS, and just because I have been part of the ATLAS experiment for a very, very long time. Back in 2006, I was able to start the group that was the first Colombian group that participated in ATLAS. And even though I left, this has continued on and grown, and many people are still working on this experiment here from Colombia. So it's one of the 2 general purpose detectors, and we can call it a cathedral just because of its size. We're talking about a massive instrument. If you ever have the opportunity of going there, it'll be fascinating. It's a cavern, again, 100 meters underground, 46 meters in length, 25 meters height. You feel tiny. But this massive detector is made of millions of very tiny things. Every single element there has to be able to detect a single particle. And to be able to do this, we need to use something like 3,000 kilometers of cables that will take the signals that are measured in each of the different parts of the detector. It's massive. It weighs 7,000 tons, more than the Eiffel Tower. And it has a whole bunch of people working on it. So we're going to be filtering through what is called the trigger system, all of these collisions, so that we can store just 1 in 200,000 collisions in real time. And as I said before, July 4th, almost exactly 14 years ago, the Higgs boson was found. After 50 years, essentially, 48 to be exact, of searching for it. It had been postulated by Peter Higgs, a Scottish physicist, and a few others that had some other ideas, 2 Belgian physicists as well. And really, really incredibly, once the LHC was turned on, it was actually really fast, in which the Higgs boson was discovered. And it was discovered by looking at how it actually decays. It has basically all the same physical parameters of the electron, except that its mass is much, much larger. And it's with the last two, the Higgs decay to the ZZ and the Higgs to 2 photons, that the discovery of the Higgs boson was made, with relatively limited amount of data, 36 inverse femtobarn, just to be precise. But that was a massive discovery. And when this was announced, these physicists that postulated the existence of this Higgs boson were actually in the audience. It was extremely moving to be able to see the reaction of their discovery. So that's the map. But I said a good map has to tell us what it can't really tell us about. What exists at the fringes of the map that we don't really know. Where are the dragons, if you want, if you refer to medieval time maps, okay? So the standard model is a great triumph. I would say one of the strongest intellectual triumphs of its time. But it has its limits. As always in physics, we have to understand what is the range of validity of our results. That is crucial. There's always a range of validity when we're measuring. So it's very well known that it cannot explain dark matter, it cannot explain dark energy, which make up, in fact, the largest fractions of the energy density of the universe by a lot. It can't explain where's the missing antimatter, which is what I started with, and it can't explain quantum gravity. So those are the limits of the standard model. So how do we go about trying to explain this fundamental problem of the missing antimatter if we can't get it to work within the standard model? So I'm just going to tease you around this with a hypothesis. This is what we do all the time. We build a hypothesis, then we try to test it, and if we can prove it through these tests, these experimental tests, as we are physicists, then, we're there. We got the result. We won. But before going into the details, I just want to show you, since I finished my PhD, it's been now more than 3 decades, and here are some highlights of major discoveries in the fields of particle physics and cosmology and gravity in the last 30 years or so. And these can be clustered around, as I said, understanding better the universe, understanding neutrinos, these very, very, very light particles that interact almost with nothing, but that are crucial in the universe and in astrophysics as well. Of understanding the Higgs and its very high precision properties as well, and understanding these ripples in space-time from gravitational waves. And I'll come to that further on. So, we have fantastic results in 1998, both of supernova experiments indicating that the expansion of the universe actually was accelerating. That nobody expected this. We had at the same time the results in Super Kamikande in Japan explaining the neutrinos would have mass, and that would induce neutrino oscillations, and so on and so forth. I'm not going to go through the full spectrum, but the point of this slide is just to tell you physics is extremely interesting and enriching, and there are discoveries that are happening around the world with a lot of people dedicated to having these discoveries being made. So, how do we go into windows of physics beyond the standard model, what we know? There are 3 basic frontiers that we can consider. One of them is the energy frontier. So this is what we do at the LHC. We build a collider, go to high energy, see if we can detect a new particle that comes out of the collisions that are happening there. And then once we've been able to identify these new particles, we really want to understand it really well. That means measuring all of its properties as much as we can. So from that, we're going into what is called the intensity, the precision physics regime. But it doesn't have to occur necessarily only in colliders. It can happen in many other settings. It can happen with rare decays. So you have, for example, we've been searching for decades for proton decay. So how do we do that? We have a setup in which we have many millions of protons, and we wait. We wait to see if one of these protons will decay, and that's how we can put a lower bound on the proton's lifetime. And of course, we have the cosmic frontier. The more we understand the universe, the more we can understand how the confluence of these three frontiers can tell us more about new physics beyond the standard model. So let me go back to each one of these frontiers very briefly. So the cosmic frontier. Planck was really the ultimate experiment measuring the oldest light in the universe. So we have the Big Bang, we have the particle reduction, we have the universe continuing to expand and cool off. Then comes that period of recombination in which the atoms form. And finally, light is transparent in the universe. That means that light can propagate over very large distances. So large that we can go back to that very early time of the universe, 380,000 years after the Big Bang. And we can measure that. And that's what Planck did. And it can measure the variations in temperature of the light and polarization. And from there, conclude a whole bunch of information, physics information, about the early universe. And I'm not going to go into all the details. There are people in the audience that are experts on many aspects of this. But what I want to focus on is that there you are able to measure what would have to be this ratio of the baryon to the photons. And it's this number, 6 to 10 to the minus 10. So you have one extra matter particle for every billion of pairs of matter antimatter. One for every billion. It's tiny, but it's crucial. So, at the same time, back in 1967, Andrei Sakharov, he was able to formulate what were the necessary ingredients to be able to produce this matter-antimatter asymmetry. And there are three fundamental ingredients. One would have to have, in the theory, some form of baryon number violation. Because if you don't violate baryon number, there's no way to produce an excess of baryons or antibaryons. Baryons are just any particle made up by quarks. You would have to have a departure of thermal equilibrium as well, because if not, the thermal abundances of particles and antiparticles would be exactly the same, so you wouldn't be able to have an excess either. And crucially, you would have to have a violation of what's called CP. CP is a discrete symmetry, in which the charge C symmetry is a charge conjugation symmetry with just changing particles for antiparticles, and D is parity, is a discrete symmetry with just inverted space. And if you were not to have this, particles and antiparticles will behave exactly the same always. And so there is no way that you could have an excess of matter or content. No way. Now, he was very clear. He formulated these are the absolutely necessary ingredients. So great. Let's go back to the standard model. Now, we're talking about the 60s. In the 60s, the standard model was being set up by Glashow, Weinberg, and Sloan. It turns out that a few years after that, we could see, hey, the standard model actually does have CP violation, but it's too small. Way, way too small. Or just a magnitude too small. And it cannot explain this number, this ratio of baryon to photons. So we definitely, there's no way around it. We need new physics beyond the standard. What is it? We don't know. So we need to think about it and try to postulate a hypothesis of what that can be. So that's the first frontier. The second frontier, precision measurements, or the intensity frontier. And I'm going to focus on only one type. And that is really a property that we know that our fundamental particles have, the electron in particular has, which is the electric dipole moment. The electric dipole moment is intrinsically a manifestation of CP violation. And it really is just a asymmetry in the charge distribution within the electron. It's incredible that we can actually perform an experiment of such high precision to measure this. And we can put an upper bound. We haven't been able to measure the actual value, but we can put an upper bound. Now, what happens is that the standard model predicts a much smaller value for this electric dipole moment, given the CP violation that is intrinsic in the standard model. So when you add new physics and you add a new source of CP violation, what you would expect is that it would induce a larger value of the electric dipole moment. So what happens when you put an upper bound on the electric dipole moment, and you don't measure it, but you put an upper bound, in fact what you're doing is you're getting rid of a whole bunch of new physics that were predicting a larger value than that upper bound. And that's good. That's good when you're able to rule out a whole bunch of additional theories that cannot satisfy this experimental constraint. Now, it's really a powerful and completely complementary way of looking at physics beyond the standard model from the first frontier. And then the third frontier. So I already talked about energy. We can always try to go to higher energies. And in fact, in the third run of the LHC, we increase the energy a little bit more, try to see some other particle. But even without that, what we're doing right now is accumulating a whole bunch of more data. And more data gives us more statistics, and more statistics allows these rare events to pop out as well. So by studying very closely the properties of the Higgs boson, we can try to understand if there's some deviation from the standard model. And in particular, I want to think about what couples the Higgs boson to the fermions is called the IPhO coupling. And in the standard model, these IPhO couplings are real numbers. But you can build models which these are now a complex number. And if that occurs, because these IPhOs are complex, then the Higgs can decay in a CP violating way, or can interact in a CP violating way with paired fermions. And that would be one hypothesis in which we could build a way of having a matter-antimatter asymmetry. It would have a clear signature in the decays of the Higgs, say, to a pair of towers at the LHC, and it could be measured at the LHC. So wouldn't that be great? So that's my hypothesis. Let's work with that. Let's see. So run 2 and have the LHC measure the IPhO couplings of the tower for the very first time. But still with a lot of error. That's why running more, getting more data will reduce error. We'll have more accuracy. We'll be able to see if we are going to allow this physics that could allow for a variation in the measurement of the value of the IPhO coupling that is different from the standard model value. Okay, so let's try to bring all these 3 frontiers together and see if we can build a really compelling hypothesis. So let's try to do this in the framework of what we call the standard model effective field theory. The analogy is that perhaps there is some additional new physics that really is relevant at very high scales, much higher than even the energy at the LHC. But what we can see at the LHC are some imprints of that new physics that is relevant at the very high scale. It's like the analogy of somebody has thrown a stone into a pond. You never saw the stone, but you only see the ripples in the water. So that's the analogy. And what I'm trying to say is we can build, in the spirit of this, we can build a model in which we can have these complex IPhO couplings of the Higgs to the fermions, and then we try to constrain it through the cosmic frontier, through the intensity frontier, and through the measurements made at the LHC. And the question is there a fermion IPhO coupling all of the constraints from all of these different types of physics. But before I give you the answer to that, let me go back to what is actually the way in which you would produce a matter-antimatter asymmetry with these complex IPhO couplings. So I have to go back to the electroweak phase transition. So remember, the electroweak phase transition is what broke the electroweak force into the electromagnetic and the weak force, right? And gave mass to particles. But actually what happened, we're at 100 GeV in temperature in the universe with a plasma of all these standard particles. And all of a sudden we have this phase transition. If it's a first order phase transition, it occurs through bubbles. Bubbles of the new phase that are created and then they expand to fill the universe. But these complex IPhO couplings have the fermions interacting with the bubble wall that has been created in the phase transition in a way that produces an asymmetry. And it's very complicated to explain. I'm not going to go through all the details, but the fact of the matter that it generates an asymmetry, more matter than antimatter, through these interactions. And when the bubble fills all space of the universe, that asymmetry gets frozen in. It cannot be changed afterwards. Okay, so that's the mechanism. So, it would be natural to think, hey, the top part has its largest mass. The interaction of the Higgs boson is proportional to the mass of the fermion. So, wouldn't it be natural for the top part to be the one that is producing the matter-antimatter asymmetry? Unfortunately, it's ruled out. Why? Because of the electrified movement of the electron. To have a large enough value to produce the asymmetry is impossible because you are already ruled out from the EDM. Similarly with the bottom part. Hey, then you think about the heavier version of the electron, the muon. Turns out it's fine from the electric dipole moment perspective, but it's actually the decay of the Higgs to a pair of muons that has been measured at the LHC that rules that out. However, the tau lepton survives all of the constraints, and you can produce a large enough matter antimatter asymmetry. So I want to be very careful here. I want to emphasize. I made a hypothesis of changing the standard model by adding complex IPhO couplings, and then I put it to the test. Can it produce a large enough asymmetry? Is it compliant with the measurements of the electric dipole moment? And is it compliant with the measurements of the Higgs physics, and Higgs in particular, Higgs decays to tau to allow for all of these constraints to survive? And it does, it works, but it's just a hypothesis. I still need to prove. How do we prove it? So that's the smoking gun. If that CP violation exists in those IPhO couplings, then we should be able to measure that CP violation in that decays of the Higgs to 2 taus. There would be a complicated measurement of the angular distributions of the tau lepton decay products, because the tau also decays. It has a very, very short lifetime. We can see the decay products of the tau within the detector. So a non-zero asymmetry in these tau lepton decays would confirm that you have a CP violating IPhO coupling. And if it's large enough, then it could also provide an answer to the matter-antimatter asymmetry. So we have, from the current LHC, the first constraints, and it's starting to shrink the available region of values for this complex IPhO coupling of the tau. We will have the Honolulu LHC, so we've now started the shutdown, going through the upgrade of the Atlas detector and the other experiments as well. And in 2030, we hope to switch on again and get 10 times more data. 10 times more data. Isn't that amazing? With the amount of data that we've been able to have since the LHC started, we've been able to measure a whole bunch of things and made a major discovery. A lot of new other discoveries as well, but not a major one as the Higgs boson. But now we will have 10 times the amount of data. And as I said before, one of the things we really want to do is to understand if there's some rare decays, things that we really need a lot of data that can only be seen once we accumulate enough of that data. And then there are projects for larger colliders, different colliders, that could continue this exercise of measuring with higher accuracy all of these variables of the standard model. Okay, so we have a hypothesis, which we are fortunate, it's falsifiable. There are many other hypotheses out there. Some can actually produce the varying asymmetry, but the problem with many of them is that they're not falsifiable. So we can't tell. And we will never be able to tell if they are the right answer. This particular example, and it's just an example that I gave today, is falsifiable. Let me go into a little bit of a different routine. I'm going to have to speed up, I see. Let me talk about gravitational waves. This is another major discovery. 2015, 100 years after Einstein had postulated that this would happen. He postulated very clearly with his general theory of relativity that if you have massive accelerating objects in the universe, they would warp space-time. And that warping of space-time then propagates through gravitational waves in space-time. And they will travel at the speed of light. And if we could build a smart enough detector, we would be able to identify them. It took us 100 years. Fascinating. What are possible sources? From astrophysical sources, we can have mergers of black holes, or neutron stars, supernovae, other things, right? The level of precision is, again, outstanding. We're measuring a difference in a distance of the width of a proton over 4 kilometers. That is amazing. That is just amazing. And we're seeing a signal. The first signal was only 0.2 of a second. Now, of course, you need to do this with multiple detectors because you need to be able to validate that everybody saw the same signal. The other benefit of having multiple detectors is that you can actually pinpoint the direction in the sky where the source came from. And so now we're building maps, other types of maps, of where are all the sources of gravitational waves. And I'm not going to skip this slide. There's more details on how you actually do this measurement, but it's really, really fascinating because just the stretching of space-time in one direction of the interferometer and the squeezing in the other makes the perfect cancellation that should occur does not occur anymore, and you get it. So that's that. But I want to tie this back to the matter-anti-matter asymmetry. Turns out that there could be other sources, cosmological sources of gravitational waves. There could be from primordial inflation. We don't have a detector really proposed yet that we know that will be done or built, at least in my lifetime, to measure any possible source of gravitational waves from primordial inflation. You can have cosmic CERN vector, but let me go to electroweak phase transition again. If we have a first-order electroweak phase transition, so that's when the electroweak symmetry breaks. If it's a first order, then it would generate also gravitational waves. And the most interesting thing is that it's going to generate gravitational waves in the frequency range of one of the proposed experiments in space, the LISA interferometer. So if we are able to see a signal within the frequency range of LISA that will start somewhere in 2037, then we will be able to correlate it to the electroweak phase transition. We have very different physical measurements. One from Planck, looking at the earliest light of the universe that we can measure, and now gravitational waves that maybe can give us information about the same physical phenomena. I want to go in two different directions very quickly. I know I'm running out of time. But we're in the full hype of AI. AI is everywhere. It's going to be even more pervasive in our lives. But I really want to take a step back with all of you and highlight that it's not AI for physics. So I use all these tools that are there, AI for science, AI for my daily life, AI for my administrative tasks, AI for this. It's really the opportunity of these fundamental physics concepts of physics for AI. And we see it already, from statistical mechanics to something that's very technical, as the normalization group in high energy physics, to phase transitions that I've talked about, liquid phase transition for a long time, to quantum tensor networks, to spin glasses. All of these, the fundamental math and physics behind this, are being currently applied in the deep neural networks. But the interesting thing is how much more we can, with our really deep understanding of physics, utilize these to transform the architectures and algorithms implemented in AI. So I leave that with a challenge for all the younger generation. I'm not my time anymore. Other people should work on this. But it's fascinating. And then the quantum frontier. We're in the midst of a second quantum revolution. We had a first one. It was a major, major revolution that transformed technology, communications, and our ability to measure things in fascinating ways. But we are now in this other quantum frontier. So, in comparison with the usual bit, which is binary, two only possible states, we have the qubit with infinite states, made up by a superposition of two states, right? Any linear combination of these two states. And that just transforms completely. It transforms quantum computing. It transforms quantum cryptography. It transforms quantum sensing and quantum simulation. We are going to be able to do things that we could not do with classical computers. For example, advancing drug discovery, understanding protein unfolding in ways that we can't do right now because we're limited by the computational effort. Of course, a lot of more technology advances have to occur. We need to reduce the logical error rate more, and so on and so forth. But at the same time, we're going to transform all of our systems of communication. So this is another area of fascinating development that I clearly encourage all of you to work on. And I don't want to stop without telling the human story, because of course physics is a science, and we all really are fascinated by doing science. But it's also a human story. And there are two dimensions to this human story. One of them, of science as a team sport. These massive collaborations, like the Atlas experiment, like the LHC, bringing people from so many institutions and countries from around the world, trying to solve a puzzle that has been decades, posed for decades. And on the other hand, have individual scientists that is able to have a breakthrough. And we stand on these shoulders of giants, as Newton did, way back when. And I just want to acknowledge that Peter Higgs, of course, has been fundamental for all of the science that I've been doing for a long time, somehow, because it's really at the core of understanding the matter and antimatter symmetry. But Peter Kenny and Fabiola Gianotti as well, who were Atlas spokespersons, to really led the experiment through decades of preparation of getting it to the work and to finding the Higgs boson. Amazing. And Fabiola then continued after being the spokesperson to be the Director General of CERN until last December. And I come from this region, I'm from Colombia, I come from Latin America. It was my privilege to be able to coordinate with a great team of people the first Latin American strategy for high energy cosmology and astroparticle physics. We brought together people from more than 10 different countries. And we built about 5 years ago this first strategy, identifying in which areas we were active, which were the experiments we were participating in, which were the proposed experiments. We're going to hear talk about Auger, which is one of the important astroparticle experiments occurring in Latin America. But really in the southern cone of South America, it's the ideal atmospheric conditions for many, many experiments that are occurring there. And our colleagues from Argentina and Chile, with a lot of international participation as well, are doing some massive experiments there. So it's fascinating. We now have the second version of this strategy that's just been also postulated, and I'm really happy to continue to support this effort. Okay, so this is the number you should all remember from now on, because this is the reason we are all here. 6 and 10 to the minus 10 baryon to photon ratio of the universe. I'm going to read this. That tiny, improbable number is the reason matter won over antimatter. It is the reason stars could form and burn for billions of years. It is the reason planets coalesce, life emerged, and civilizations arose. It is the reason you are sitting here right now. And the answer may already be waiting for us in the data. Thank you very much. I don't know if there are any questions, or if we have time for questions. Do we have time for questions? Yes, please.
Yeah, okay, wait a minute. Wait.
In one of your slides, you said that the dipole moment of electron has been given upper bound of like some e centimeter, like minus 29, I guess. And so I wanted to ask, how do you define electric dipole moment for a charged species?
Do I define electric dipole moment for what?
Like for example, like a charged species, how do you define an electric? Like an electron has a charge, right? So how is electric dipole moment defined for it?
I'm sorry, I don't understand exactly the question. Can you try to ask again?
The dipole moment of an electron
Yes.
is how is it defined? Because normally we define dipole moment when the net charge is zero.
Yeah, but so you can have asymmetric distribution of the electric charge within the electron, and you can see that, and you can also formally write the term that will give you the electric dipole moment of the electron in theoretical particle physics. Yeah, but physically, it's because you have an asymmetry in the charge distribution within the electron.
So, for example, if the charge distribution is uniform, then and it's like uniformly negatively charged, so then the dipole moment is zero. Is that correct?
No, in the standard model, it's not exactly zero. I mean, to first approximation, yes, but you have higher order corrections that make it non-zero.
Okay. Thank you.
All right, well, thank you very much.
I have a question.
Yeah.
Is there a probabilistic factor in the breaking of the symmetry? So could it have been possible that the symmetry did not break?
No. The symmetry is broken. There's no way around that. The electroweak symmetry is broken. As I said, the evidence of this is the real difference between the weak force and the electromagnetic force.
Thank you.
Thank you.
Alright, so the questions, if answers are already beautiful, questions are even more. And now we're moving on with a question talking about quantum biology. Thus, nature uses the subatomic physics. So, we'll be receiving Dr. Alexandra Olaya-Castro. She is a titular professor at UCL and the first Hispanic woman on receiving the Maxwell's Medal. And also the IOP from the Physics Institute. She will be facing the limits of the traditional science, explaining how plants and bacteria, they use the quantum coherence and the molecular vibrations to transport energy in photosynthesis with a perfect efficiency.
Good morning, everyone. Buenos días a todos. Thank you so much for having me here. As you can tell by my accent and my name, I am also Colombian. And I always take any opportunity that is offered to me to come back to Colombia and share with you my learnings, my science, and to just simply experience this beautiful country as much as I can. I left Colombia a while ago, but Colombia never left me, so Colombia is always with me. What I would like to tell you today is a story. So it's a story of doing science and what is involved with doing science and the science that I do with many other people. I work for University College London, which is one of the top universities in the world, and it is based on a very vibrant city, which is London. This is a picture of where UCL is located. So if you've been in London, because I know this is an international community, it's very, very close to King's Cross, and there is not a lot of green like it is here in Bucaramanga and Santander, but despite of all, it's a green city, and that I love. This is the main quad in University College London, where I work since 2008. It's not so green now, they removed the green, but it is still a beautiful front, just located in the middle of London, very close to the British Museum. So if you ever buy London and buy UCL, please come and see me. Now, while my story has taken me to UCL in London at this stage, it didn't start there. It started in Bogota, where I was born. And the picture that I showed you is when I graduated from my 5th primary school. At that time, I have always been a person who loved maths, but I had no idea anything about physics. And it was not only until the final 2 years of high school, so when I was 13 years old, that I came across physics. And guess what? I hate it. I hated physics because it seemed like a maths, but it wasn't maths exactly. It was something like maths with something else that I didn't understand. It's like exactly what it was. And imagine if you are like you are high achievers, so you are here because you are high achievers. And I have always been very good at maths, but then I came across physics and I failed physics. So I hated it even more because it was the first subject that I even hated. There was another subject that was also part of my affection, which was biology. Biology and physics, not the thing that I wanted in my life. Paradoxically, it's the thing that I do now and that I love. And I'll tell you how I came to that. One more thing, because I hated physics, but I'm always a person who loves challenges, I then during the summer decided, okay, well, I've always been good at math, how come this physics is gonna be so difficult? And then I started studying physics by myself. And that is when I understood that physics wasn't just maths, was not even maths at all. It was a way of seeing and exploring the world. And when I understood that, I absolutely fell in love with physics. So since then, physics has been every part of my life. every day since then until now. And the first part that I came across physics, and then that I revisited when I was at university, were the laws of Newton, Newton's law. I didn't understand anything about them. I understood much better when I started studying by myself. I started teaching to my classmates about the Newton's law, but I didn't have the chance that you did, because in the school that I studied, the International or the Physics Olympiad was not known at all. What was that? I didn't know anything about that. Nonetheless, I fell in love again, and even more with physics when I understood a little bit of the Newton's law. And what I'm showing you here is something very interesting, because just in March, I came back to Colombia and I visited the National Library in Bogota. And in that National Library, they hold one of the earliest English translations of the Principia Mathematica from Newton. And you cannot see it very well, and I don't have a pointer to show you, but if you look at, here I can point with this laser. At the bottom of the Principia, there is some handwriting, and what is written there in Spanish, but the translation to English is excommunication reserved against whoever usurps it, which essentially means whoever took this book without any authorization will be excommunicated. And that was in the 18th century. Why was this important for me in March when I came back here to Colombia and I found this first copy? Because I had never seen it before. I went to Oxford to do my PhD. And it was really surprising and exciting to see the Principia of Newton there, and that I could hold it and I could read directly what it was in there. And it reminded me of the love that I felt with physics when I understood these three laws. So simple, so powerful. Again, I understood what physics was about, and it was essentially making sense of the world in ways we cannot do it in any other form. But that wasn't the only thing that I loved about physics. Sorry, can I just move this? I just don't like being behind this thing. But that wasn't the only thing that I loved about physics. As I started to fall in love more and more of physics, I studied physics, not just what I was doing in high school, but what I loved just reading about physics. I remember one day having a conversation with my high school physics teacher, which was explaining why it was difficult to see electrons. And in very simple words, he was explaining, trying to describe the uncertainty principle in quantum mechanics. And I remember that he mentioned that we could never see the electrons. And that for me was like, how come? How come? It's the most fundamental structure of matter and we cannot see the electrons. And I remember that I stayed with that question in my mind. There was no internet at the time, so it was very difficult to find information about this. And I dreamed that I have seen these electrons. And I dreamed that I could see exactly how they look like, how they move. I knew everything about the electrons. So I went up extremely happy because I knew how the electrons look. Of course, when they ask me, how did they look, I didn't remember, because as dreams happen, you cannot remember. But interestingly, in 2013, this is exactly that stayed in my mind. In 2013, I came across an article by some colleagues in the Netherlands who have managed to image the electron or the orbit of the electron in the hydrogen atom. So the image that you see there on the screen is not exactly the full electron, it's just simply the distribution of charge that was possible to image by exciting the hydrogen with a two-photon excitation and then exciting it further to higher levels of excitation and then sending another pulse to produce an interference pattern that then they can image and present this. Excitingly, we could actually see the electrons. So that question that started when I was 17 years old, it never left my mind. It was not what I did for my PhD, it was not what I did for my research later, but it never left my mind. So finding in 2013 these physical review letters showing how this seminar in Amsterdam was imaging that electronic density, again, made my heart beat and reminded me ever and ever again on the beauty of physics. Now, I just want to share with you a little bit of my path here, because as in every journey in science, and Marta was saying, science is a human endeavor. And I want to share with you what that human endeavor looked like for me. So I did my undergraduate in the Universidad Distrital Francisco José de Caldas here in Bogotá, and I studied physics education, which means I studied to be a physics teacher. But at the end of my studies, I just wanted to continue learning physics, so I wanted to do a master in physics at the Universidad de Los Andes. And when I finished this master, I not only wanted to learn more physics, but I wanted to do physics myself. So I managed to get a scholarship to do a DPhil in physics at the University of Oxford when I first came across the idea of quantum coherence. Then that idea never left my mind, and I have dedicated my life to understand quantum coherence in many different systems. As in any academic career, I wanted to have an independent fellowship as well in Oxford, and after that, I just wanted to do my own ideas. I just wanted to work on the research problems that I wanted to address. And being a Spartan as I am, I just said, no, I just want to do this, and I continued in that path, and I became the equivalent to assistant professor, but in the UK lecturer at University College London. Life has many dimensions, and science was not the only part. I got married, I had my first child, then I had a second child. I continued doing my research, and this has been the path. The main thing that I want to highlight about this path is that there has been one key constant. The fact that it's a path that I have not traveled by myself. It is a path in which I have worked with colleagues, mentors who have supported me. And as you can see here in the image, if you know him, there is Professor Eduardo Salamea, which was my professor at the University of Francisco José de Caldas here in Bogotá, whom I learned classical mechanics. Those principles of Newton that I started studying when I was in high school, I then finally learned them, you have to, with Professor Eduardo Salamea. This is to acknowledge the colleagues that have played a very important role in me being here today. Now, this is not the only part, and not the only people that have made it possible for me to be here. My family has played a very strong role. Once you have kids and you are doing your academic career, it's very difficult to manage everything. This is true for women in science, for fathers in science, for people doing science, but in particular challenging when the care of the children are very much in the hands of the women in science. So it is not easy to get around to do science when you have to juggle so many things, but I have been lucky enough to have a family that supported me at every stage and then stopped their life here and went there to support me, including my mom, my dad, my sisters. Now, another constant in my life is as the people that have supported throughout this journey in physics, there has been one thing that has happened at every turn, and it's the kind of questions that I ask and that we can ask. Now, when you're in A-levels, high school, a lot of the emphasis is in solving specific problems that are given to you. Someone asks a question, tough question, and you solve that question. But not the majority, we can discuss that in a little bit. But for me, the journey became to ask the question, to ask a question that will make significant and that will contribute knowledge if I answer that question with my team. And this brought me to this sentence that Carl Sagan wrote in Cosmos, and it's, we make our work significant by the courage of our questions and the depth of our answers. And this is what I have dedicated my life in the last 20 years, to ask the toughest questions that I can ask in the fields that I research, and to provide depth, answers with depth and predictive power. The image that you see there is an image that I have taken from NASA. And just by coincidence, it happened to show Colombia there at the top. Now, it is a beautiful image because it reminds us of our beautiful planet, which is Earth, and how life is supported on Earth. So I would like to tell you how my research is now providing some insights in understanding the depth of that question, how life is supported on Earth. Now, this is not a question that I myself alone have asked. This is a question that many scientists have asked throughout the history of science and our understanding of the world. But I like in particular this sentence, because again it has to do with the electrons that I have been fascinated forever. And in 1937, the Nobel Prize was given to Albert Seghaiordi. And in a long essay, one of the things that he was describing is that he was describing the importance of oxidative and electronic reactions for life. And then he wrote, "Life is nothing but an electron looking for a place to rest." But I always thought that there was another sentence that will complement this. And life, besides being about electrons looking to where to rest, it requires a sophisticated handling of energy quantum. Do you know who said this? Have a guess. One of you? Anyone? Yes? I think. And I love that you get that answer. Often when I ask this question, people raise their hand, oh, Albert Einstein, because he was talking about the photons, or Bohr, or anyone else. No, it's just him, and it's a way of summarizing precisely what my research is about. My research is about understanding how molecular systems manage this energy quanta in a very sophisticated manner to support processes, fundamental processes on Earth. Now, this question for how life processes might be supported by atomic and molecular processes that are described by quantum mechanics is not just a recent question. It's a question nearly as old as quantum mechanics itself. And there are two particular articles that kind of remind us that this happened, this question started a very long time ago. One is an article that was written by Bohr, that he presented to a community that it was mostly men, scientific men. And the other one is the book that Erwin Schrödinger wrote that was about what is life. Now, this book is very well cited, but I don't think it is very well read. But it's these two contributions. We're asking how can we use light to control molecular processes in systems, in biological systems. And the what is life that Erwin Schrödinger asked well beyond how the structures of biology support quantum mechanics and how this at the same time supports biology. Now, while these questions started nearly at the same time as the quantum mechanics was being created, and they have evolved, and the way we have answered these questions have evolved significantly in the last century, in particular in the last 40 years. We have new experimental and theoretical techniques that allows us to investigate biological systems in more detail. We have an exceptional progress in quantum science and multi-scale approaches, and we have redefined the questions of interest. So the question that I am interested in is how can we affect biological processes by understanding and modifying the molecular scale. The image that you see, for some reason, moving on the screen in that way, is showing a cryptophile algae that does photosynthesis, and the zoom shows the molecules that absorb light in those cryptophile algae. And the question we're interested here is a difference, so that's cryptophile algae that does photosynthesis, but what you see here on this screen is a similar molecule. This is a biomolecule similar to a collection of chlorophylls, but these ones are the ones that you find in bacteria, so it's a collection of bacterial chlorophylls. The size of this complex is around 5 nanometers. This complex absorbs a photon. It creates an electronic excitation, and that electronic excitation gets transferred, which means it de-excites and excites another molecule in this membrane, and the chemistry of photosynthesis starts when this excitation, this electronic excitation, reaches a reaction center where all the chemistry occurs. Now, one of the key aspects of this process is that it's happening in a femtosecond to picosecond time scale, while the time scale in which this energy will be lost to the electromagnetic environment is nanosecond. So it's a very, very fast process. And what this means is that then, in very low intensity, almost every single photon generates an electronic excitation, and that effectively will generate the chemical reaction that starts photosynthesis. No man-made system has ever reached the quantum yield that these systems do. So it's no surprising that we want to understand exactly how they work. But besides understanding how they work, our interest is also to connect how the behavior that being described at this molecular level, for which we need the laws of quantum mechanics, will affect higher levels of complexity in the biological system. And that is the main aim of the field, of a frontier field that has emerged in the last 50 years, which is quantum biology. It's essentially to try to connect in a causal form the quantum processes that are happening here with processes that happen at different levels of organization in a biological system. My background is fundamentally quantum optics and quantum science, so I focus very strongly on understanding quantum phenomena at this molecular level and connected it just to the next level. But with a group of interdisciplinary scientists who are trying to connect it all the way from the molecular level to how a bacteria, in this case photosynthetic bacteria, might survive in different light environments. And to do so, then we have expanded the remits of the questions that we investigate. So we not only investigate what are the quantum processes, and I will illustrate in a second what I mean exactly by those quantum processes at that molecular level, but we are also now interested, okay, once you know and if you understand those molecular processes, how we can use quantum technology to affect those processes and control those processes, because that is one of the key aspects that quantum technology can offer us at this moment. But because this is a biomolecule that you find in a biological system that can be modified with synthetic biology, essentially by changing and doing mutations to the DNA of this system, which means that we can use biology to, in a way, control the quantum properties that will affect the system. So this is an integration of quantum science and bioscience in ways we haven't done before, but that we can do now because we have advances in the quantum science, we have advances in synthetic biology, and we have advances in the conceptual understanding of what is truly quantum in these systems. Therefore, my research group is now addressing questions in these three regimes. And what I would like to illustrate now to you is the kind of research that we do. Now, whenever I talk about research, I cannot talk about research without at least showing the people who actually do the research. This is a team effort, and this is a group of early career researchers, PhD students. There is a long list of master students that are not mentioned here, and postdocs who have joined me in this effort to answer to address these three pillars in the region of quantum sciences and biosciences. My most current team is the one that you see here. It's an international team, so a Colombian student who just finished his PhD and passed with minor corrections. A student from Iceland who is now working again with me because he's fascinated with these systems. A student who just finished their PhD and is going into AI. And two students who just recently joined and they're still figuring out what they want to do. As I mentioned before, this is not a question that physicists alone can answer. This is an endeavor that has brought together at least 4 academic communities: the biological physics community, which is the traditional community that has investigated this problem with the physical chemistry, but is now joined in a very productive way with the quantum science community and the quantum chemistry community. All of those are communities that address the problem in a different manner, so ask the key question in a different manner, but that to be able to answer the fundamental question, which is how we can affect biology by modifying the quantum level, no single team alone could do it. And it needs the effort, the joint efforts of these different communities for that question to be able to answer, to be able to be, giving an answer that is satisfactory. Now, what I want to describe to you is what exactly, so why this quantum phenomena? What exactly are these quantum phenomena that we are interested in? Just in very simple terms. One thing that we know, and we have known for a long time, is that photosynthesis, of course, exploits quantum mechanics. The electronic structure of these molecules can only be explained and described by quantum mechanics. And we know more about those processes that are happening in those molecules because we have advances in experimental techniques that allow us to see many molecules at a time and investigate them in fast time scale. This is ultra-fast multidimensional electron spectroscopy. But we can also see these molecules at a single molecule level. This is an image of a collaborator that I work with at the University of Cambridge, and we have a joint project in which he was adventurous enough to follow one of the theoretical predictions that we did, and he wants to confirm whether our predictions hold at the level of a single molecule. I don't have an answer yet because it's a project that we have ongoing, but we'll see. I'm excited to see the answer that he will give. What we focus fundamentally, because I'm a theoretical physicist, is in producing these theoretical frameworks that have predictive power and that have explanation capacity. So not only computing what the answer would be, but actually explaining and producing a conceptual understanding of what is going on in the systems. Just to give you a little bit more of the physics, the quantum physics that is involved here, and that is well understood and known, and there is no controversy around. If you imagine these structures that you have here, the red and the green, imagine that these are two chlorophylls. In reality, these are other kind of pigments, but for the purpose of this illustration, imagine that these are two chlorophylls, and they are interacting via a dipole-dipole interaction. These are transition dipoles, which means that you only have a dipole once each of these, which you can see as a two-level system, goes from the ground state to the excited state. Then there is a distribution of the electronic density there, and then you have a transition dipole. So it's not a permanent dipole, it's not a transition dipole, but then it excites that molecule, and then it excites the other molecule. And with this laser here, it de-excites this molecule, and it de-excited because they are interacting in an interaction that goes to one of the R3. Now what is important is that due to that interaction, two different states appear, which means that these molecules can absorb light that is different from the individual molecules. And that is only something that you can explain fundamentally by quantum mechanics. So in this case, there is no controversy. It's something that is well known and that people accept, and that actually photosynthesis exploits to be able to absorb all the wavelengths in the visible. Here is an illustration of the photosynthetic structures that nature has evolved and that are able to absorb energy in all the wavelengths from the close to the UV, 400 nanometers, to close to the infrared. But there is a lot of the spectrum, the visible spectrum, that we still, that these organisms are still not able to absorb, and therefore a lot of the effort is how we can enhance these systems to actually absorb in regimes of energy that they are not yet absorbing. The work that we're doing is hoping to provide some insight into how we can enlarge this capacity for not just for natural systems, but hybrid natural synthetic systems. Until then, the story is well known, and people agree with this. But this is a field that is free from controversy. One of the key questions in the field is, okay, to absorb light, these systems, we need to use quantum mechanics to describe. But once that light is absorbed, to transfer the energy, in general it was thought that you could just simply explain that as a Markov process. As if, for instance, I had a ball here and the ball was kicked to each of you, and energy is transferred randomly until it reaches the location that it needs to reach to start the chemistry. So a random process which is simply dominated by thermal fluctuations. But what the experiments in 2008 started to show is that that picture wasn't so correct, and that actually there were quantum coherent processes, which means that as energy was transferred, some coherent superpositions were created in these biomolecules. Just to illustrate here, the best way for me to illustrate quantum superposition is an interference pattern between the, rather than matter, is the amplitude of probabilities that you could have a system in different states. And what happens with these superpositions is that they are very fragile, and when they interact, when they are completely isolated from any thermal environment, they survive, but as soon as there is interaction with the thermal environment, they get destroyed. And therefore, they get destroyed really quickly. The time scale that was predicted for destroying these superpositions in those biomolecules that I illustrated was around a few hundreds of femtoseconds. And the experiments were showing that these superpositions were lasting at the same time. Now, you can imagine 100 femtoseconds, that's very, very short time scale. But it's not a short time scale if you compare the 1 picosecond, which is the key time scale for transferring to another molecule. So whatever was happening here cannot be described in that classical way. And it was telling us that it was something that was happening at the same time scale of the process of transfer. Therefore, it was important. Since then, I would say that was since 2010, people have tried to first reproduce the experiments that were showing this, and second, try to understand and make sense of why this would be relevant for these systems. A system that in general is driven by thermal fluctuations. Why would these systems use this quantum phenomenon? We don't know yet the answer, but we have given some insights into why it is the case and why this might be important. How am I doing with time? About to finish? So, just to finish, I'll tell you the answers that, some of the answers that we have given, not just my group, but my group and other groups who are coinciding in these answers. Different methods, different ways of addressing the question, but we are coinciding in these answers. The first thing is that everything that happens in these systems is a balance act. It's a balance act between those coherent motions and those thermal motions that they compete. And they compete because they provide two different ways of transferring energy. By using these coherent superpositions, different transfer pathways can be explored at the same time. And by using thermalizing motions, energy is located where it needs to go. So photosynthetic systems seem to have evolved to exploit these physical mechanisms in an efficient manner. One of the most exciting reports that my group has produced recently is that we have shown that this balancing act happens not just when we take these molecules out of the biological system and investigate in the lab, but they are probably happening right in the cell environment. This is just one of the questions that we address. This was a question that was addressed by a student, a PhD student who she just finished, and she's smiling there because this is a photo that I took when she was notified that the results have been selected as one of the best presented in Biophysical Journal in 2025. Now, besides the ego that you might think this is about, the excitement wasn't so much for that. The excitement is because this biophysical community, who normally do not consider quantum effects to be relevant for the biology that they do, were identifying this as an important contribution, which means the message has reached that community, and that was very important for us to have the field. So that is a part of the excitement. And what she did is that there were some theoretical results, and we have a theoretical framework that is, I would say, sophisticated enough to account for the complexity of the biology, and we were able to predict very close to what the experiment was showing. That hadn't been done before. So I was very happy she graduated with honors. And the second example, just to show you what that kind of nuisance and very interesting quantum phenomena that happens there can be illustrated by this work that was done by another PhD student. In 2019, I visited California to give a talk. And when I was visiting California, I took my kids to the museum. And in the museum, we saw, let me see if this works here. Oh yeah, not yet. Here. Oh, no, that's not going. Sorry, I need to start again. Let's see if it works. Yeah, so we saw these two metronomes synchronizing. And if you look carefully, they start completely out of phase. Then at some point, they start going in opposite phases. And then at the end, they synchronize. And they synchronize because they are interacting with the same, very quickly, with the same base. When I saw this, it made me realize that we haven't asked an important question to those quantum phenomena that we were considering for these biomolecules. And it's that these biomolecules not only have those electronic excitations, so electrons in this system gaining energy and getting into a higher state, but it also has nuclear motions. And some of the nuclear motions, in general, they are very slow in comparison to the electron motion, but in some cases, depending on the energy, because of collective interactions, those electronic motions are not so slow, and they get excited with the electronic motion. So I proposed to this student, what about if we investigate something similar to this synchronization, but now regarding the molecular motions that are happening in this system. So in this case, something that happens classically actually inspired me to think of a question in the quantum domain. And we produced a paper that we presented in 5 minutes in an event in California in 2019. And the 5 minutes presentation led to an hour discussion. It has been one of the most discussed papers in a presentation of this kind. This was a theoretical prediction that people considered, oh, this is exciting because then you have changed the focus of the question. The focus is now on the electronic, not just the electronic motions, but the nuclear motions and what is happening to those nuclear motions as the energy is transferred. In 2025, a group in China demonstrated experimentally our predictions. So that visit to the museum in San Francisco led us to propose something that eventually another group somewhere in another part of the world demonstrated experimentally. So with that, I would like to just going towards the end and just say this knowledge, we've done it, and we do the science that we do in my group is because we're curious about it. This is curiosity-led research, fundamental research. We don't know exactly what the impact of this knowledge would be. We can envision that it can do many things. For instance, that it can help us to use the sun energy better, because the sun belongs to no one, and then if we can improve the ways we absorb that light, then maybe we can solve a lot of the energy needs in the world. We can also maybe create new materials that have these quantum enhanced properties and therefore reach the quantum yield levels that we observe in nature. We can maybe use improve photosynthesis to improve crop yield and therefore feed population around the world. We can even now consider using this for quantum tasks like quantum sensing. So this year there was an important, very fundamental breakthrough, which is we can use proteins as the ones that I showed to create qubits, and therefore we're very excited about that. But the truth of the matter is that we don't know this yet. That is not to stop us in this endeavor of fundamental science, which is about exploring the world and seeing the world in ways we have not seen it before, because all the transformational technologies that we have now started because someone visited maybe a museum somewhere so many years ago and asked a question no one else has asked. So with that, I would like to finish, not without saying that this journey has many dimensions. My love for physics is not my only love. Of course, my love for my family who are here, but also I have a passionate love for sports and dancing. I know that this afternoon you are going to go sports, and I'll tell you, I couldn't do physics if I didn't do tennis. Thank you for your attention. Any questions? Comments? Yes?
Hello.
Hello?
Well, first of all, I want to thank you because you really gave a different perspective about this kind of way to maybe solve issues or problems that we face every day, maybe about physics. It's really amazing, and I loved what you said about asking the correct questions. First of all, that, and then I wanted to ask that do you think that during this time, as we are achieving and getting more knowledge about, for example, quantum mechanics and how basically everything works, do you think anytime is going to be, dangerous for us to achieve this kind of knowledge that could be maybe dangerous for us, because maybe, I don't know, we saw many times that we all are humans and we usually tend to, with the discoveries that we have, we usually tend to affect us in some way. We saw it in wars, for example, with the creation of the atomic bomb, and with this kind of new knowledge and this kind of powerful information. How do you think of, or what are your expectations about the future of humanity?
Thank you so much for that question. That is probably one of the toughest questions that I have received, but at the same time, one of the simplest questions that I have received. Any scientific endeavor has definitely an ethical dimension. And us, as humans doing the science, is completely our responsibility to ensure that the science that we do is used for the benefit of humanity. Having said so, we definitely know that a lot of the scientific developments that are leading to these frontier technologies, there are many interests in this humanity that might not lead to the benefit of everybody as we would like to. Just to give you an example, with quantum technologies at the moment, there is a race, and there is a race across the world. United States, the United Kingdom, China, let me put them as three very important players in this race. And in that race, the importance of this race is crucial because it's leading to no cooperation between the countries. There is secrecy, there is an anticipation that some of these techniques can be used, for instance, to develop sensors that can eventually be used in warfare. So there are a lot of tensions in these technological developments. So the future of human, I am a particular optimist person in the sense that I might not trust the people who take those decisions, but I do trust you. Maybe it's a mistake, but I trust you because I know that there are new generations coming asking the questions that you're asking. Apart from doing the science and being very excited and being excellent at solving problems in physics and creating problems in physics, you're also asking these questions. And therefore, that gives me, I would say, an optimistic view about the future, about the idea that whatever science we do, we put the pressure for it to be used in the best manner. But yes, we need to acknowledge the tensions that are happening. I work as an advisor for the SSIC in Spain. And part of the advising role is precisely to anticipate what those tensions could be and how we might go about resolving those tensions. So, just to summarize my answer, I do see some ethical connotations that we need to anticipate, but I believe that there is enough critical mass aware of those tensions and willing to make sure that the science that we do is used for the benefit of humanity. I might be very naive, but I am optimistic. Yes.
First of all, I would like to thank you for the amazing lecture. And second of all, my question is that as a neighboring and upcoming scientists or researchers, the main question is, after all, we have faced many hurdles, of course, over time. So how can we fight and ensure that we would have a highly optimistic the achievements regarding international research?
Let me see if I understood. So how, after all this, how can we assure that we will have
International recognition within research.
So you mean because of the tensions that are happening?
Exactly.
That's a very important question. So I don't have an full answer for that, but I'll tell you the challenges that we're facing. UCL is an international university that it recruits a lot of students, undergrads and researchers from China, for instance. And mostly because the fees in UCL are very expensive and not everybody can pay them. But we used to recruit students from all over Europe, and we used to have a little bit more of access to overseas students from all over the world. Christian David Rodriguez, one of the students that I showed there, is one of the few students that I managed to bring from Colombia to the UK before these tensions started happening more and more. We're facing a lot of obstacles in bringing people to do research in areas that are identified as possible conflict, like in quantum technologies when there is a race. The way we have gone about changing this, not fully changing because there is a power outward that we cannot, which is the immigration laws of a country, but the way we have gone to this is philanthropic funding. So one of my main grants, the research that I do is actually coming from the Gordon Medina Foundation in the United States. And this is a grant that comes with less restriction than many of the other grants. With that, I was able to bring students from another part of the world. So we are facing challenges, and what scientists are doing is that we're becoming more creative in the way we ask the questions to show that this is a fundamental question that not necessarily is for war, etc., but it's a fundamental knowledge question that we need to be able to move on as a society. And second, going to philanthropic funding that has allowed us to break those barriers, because philanthropic funding, this is people who have become millionaires investing in let's say, whatever industry they did, for instance, the semiconductor industry, but they recognize to some extent the importance of fundamental science, and therefore they are willing to invest in the talent.
My last question is, what are the hurdles that you have when trying to explain how a certain scientific research is important and trying to prove that it is, for example, safe and not for war, whilst explaining it to a non-scientific community?
Yeah. So thank you for that question. And I have been fortunate in the following. I have established dialogues with many different communities, not just the scientific community, but community, for instance, of philanthropic funders, community of diplomats, community of people who are interested in science. At the moment, I am working with an organization that is called, I did a project in collaboration with them. It's an organization, it's a young organization called JESTA. And this organization precisely have realized what you just said. There are a lot of obstacles because we are not explaining, or there are not many ways in which we have communication with the people who are making decisions, the financial decisions in countries. But scientists have a very compelling story to tell about the importance of fundamental science. And therefore, this organization creates a bridge. And in October 12 to 15, there will be a summit that is bringing diplomats from all over the world because it's with the United Nations. And the summit involves one big theme, which is quantum biology in this case. It also involves quantum science. So, short answer is, I myself, my reach is, I am reaching to talk to communities that are not just my scientific communities, but I'm getting out of that bubble to be able to talk to organizations that have realized that we need to create communication between those who make the decisions and those who have created the knowledge to transform our societies. And then recognize that beyond all the fears and the tensions, there are potentials that will solve humanity problems. I cannot create hype and make a promise, oh, with quantum biology we will solve all the health problems, or we will create new computers. But what I can say is that we will provide some knowledge that, together with a lot of other knowledge, can help solve those fundamental problems that are relevant across the world.
I'm sorry for another question. You see, my just last question I asked. Yeah, last thing is that, of course, there are many researchers that have philanthropist idea or hope. So when a researcher is trying to submit his research to a certain fundraising community or a philanthropic charity, how do we know that our research won't be used or taken and used for like bombing children or in a bad way?
I mean, there are things that you can never know, yeah? But when you submit a grant proposal to, for instance, a council like, you know, for sciences here, the PSRC in the United Kingdom, in the United States, the city in Spain, name it in each of your own countries. We have a peer review system, which is not perfect. It has other obstacles that are much more tangible than the one that you are mentioning. There is a lot of bias in the way the funding is allocated. And sometimes to get your grant funding, you really have to have done your research and presented all the results. So by the time you do the research, maybe all the preliminary data are already telling the story. So this exploratory aspect of the research is a little bit forbidden there. But that peer review system, with all the difficulties and all the challenges it has, is our best bet for now for science. Because it means that we as scientists will be discussing issue science, the science that we need to do, and then there are mechanisms within these institutions to support that science creation. So I will say that I will be fearful that if I send my research, it will be used for war. Of course, it depends who's funding your research. So if your research is funded by Air Force in the United States, well, then you know what that means, why the investment might be there in certain aspects. But even so, sometimes the investment that is coming from there is a fundamental science that will have not only impact in kind of warfare issues, but it will have impact in other aspects. The truth to the matter, from my perspective, is we need to keep that ethical perspective of the scientific endeavor well up front whenever we are doing science and whenever we choose to receive funding from who we receive funding. But at the same time, we need to keep open and bringing different communities that might have different tensions and different interests together to talk. Only through that communication global, we will be able to join efforts that will drive science for the impact for the rest.
My name is from Kuwait.
Thank you so much for the question. Thank you very much.
So a love story can be everywhere. In this specific case, it was a haters to lovers. But just remember that she was the one who said it. She was Alexandra Olaya-Castro. And moving on, we are going to talk about the observatory at Pierre Auger. listening to the energetics of the universe, the most energetic messengers of the universe. He is a site manager at the Pierre Auger Observatory in Argentina. The detector of the rays, cosmic rays, biggest on the planet, with an extension of 3,000 kilometers. And we are going to be submerging in the heart of a hybrid technology from the faculty and the detectors of muons. We will find out on how the observatory is chasing those particles and ultra-energetic events and electric events in the atmosphere to solve from where they come and what to do.
Morning. First of all, let me thank the organizer of this event for having me here today. It's really an honor to be here, such a wonderful audience. And also, I would like to congratulate all the students for being here, representing your country. I hope that you are having a good time here. It's a wonderful country here, Colombia, so I'm having a very good time. So I will start my talk telling you that, well, my name is Nicolás Leal. I'm an electromechanical engineer, so I am not a physicist, but I'm the site manager of one of the biggest physics experiments in the world, Pierre Auger Observatory. So I will give you maybe some other point of view of what a physics experiment looks like, maybe the issues, how do you go from the theory in the paper, the lab, to the reality, to have a real detector placed and taken in. What you can see here in that picture is a tank, a plastic tank, that is sitting in the middle of nowhere, in the middle of the Pampa in Argentina. And that tank is currently receiving hundreds and thousands of signals coming from outside our planet. So that's a real mystery for us, trying to understand why that tank is receiving that amount of signals. So let's start by the mystery. So maybe some of you know this guy, the one that is on the left, the picture. He's a football player and he's hitting a ball. And that ball is traveling at about 50 kilometers per hour. And if you do the math with the weight of the ball, which is 400 grams, that ball has more or less 50 joules of kinetic energy. So now imagine that amount of energy that the ball has concentrated into a single proton. So in 1991, an experiment at Utah, United States, detected what is called the oh my god particle, which is a particle that arrived to the Earth and hit our atmosphere with that energy. So is until now the highest particle that has ever been recorded to reach our Earth. So it looks like I spun from the logo of the Olympics, but this is a simulation of a cosmic shower. What you see here is a cosmic ray. It's a particle that is traveling and it hits our atmosphere. They are the most energetic particles known in the universe. What we do know is that they are mainly protons that are traveling nearly at the speed of light, but they can also be atomic nuclei, ranging from helium to iron. The origin of those particles is still a mystery. And when they hit the atmosphere, they produce what is called an extended air shower. A cone is like a cascading reaction with billions of particles generated in the atmosphere. So to give you a dimension, the energy scale, we have the flux of these cosmic rays in our air as a function of their energy. And as you can see in the plot here, the flux is going downwards when the energy goes up. So here on the first part of the plot, we have a lot of cosmic rays hitting our atmosphere at low energies, low, let me say it in quotes, because it's not that low, but it's the energy of an X-ray, say. So we are receiving 1 particle per square meter per second, that range of energies. Then we have the energy of the LHC protons, which is maybe in the middle of this plot, where particles are arriving at 1 particle per square meter per year. And then we have the interesting part here below, where the energies are around 10 to the power of 18, 19, even 20 electron volts. As you may know, in the astroparticle physics, we use the electron volts to measure the amount of energy. So the very interesting part is here, but it's a challenge because the flux is very low. We have 1 particle per square kilometer, maybe per century. So these are particles that are very rare. Here you can see how extensive air shower develops. When the main particle, the primary particle, hits the atmosphere at 30, 40 kilometers up, it produces this shower. This shower is divided mainly in 3 branches, 3 parts. We have the hadronic part in the middle, which is we can say the fuel. The shower is the part that keeps producing these billions of particles, and is composed by mainly the protons and the neutrons. Then on the left, you can see the electromagnetic part, where we have the electrons, positrons, and also the photons. And on the right, you can see the muonic part, where the muons, some neutrinos are produced. This shower develops a very big footprint of several square kilometers, reaching down to the earth. So we have some open questions that we really don't know yet. The first question is, what accelerates these particles to these high energies? Where do they come from? And what are they? So we know what can they be, but we don't really know the specific particle that was creating this shower. So these 3 questions will guide the rest of the talk. I will try to answer what have been discovered in these years. So the challenge of why is this detection so hard is mainly because we are interested in that low part of the plot that I showed you before, the highest energies cosmic rays. And they are very rare, 1 per square meter per second. And why we are interested in these very rare events is because the higher the energy, the path is less disturbed by the electromagnetic fields that we have outside or in the galaxy and beyond. So the highest energetic cosmic rays can give us a more precise way to see the origin of this particle. And we cannot catch the primary particle because it's one, and it's very rare, and it's traveling and hitting the atmosphere 30 kilometers in the atmosphere, so we cannot catch it if we are in the ground. So this is why the Pierre Auger Observatory was built. The Pierre Auger Observatory is the largest cosmic ray detector ever built. It has a surface of 3,000 square kilometers. To have that amount of surface, you need a place where the surface of the land can be very flat and very accessible for this big area. Each dot that you can see in this plot is a tank, as shown in the first slide. We have 1,660 tanks deployed in the ground. And we also have 27 fluorescence detectors. I will tell you the details. But let me first show you this. Building the Pierre Auger Observatory was not easy, because each of those tanks that I show you in the plot, the position is determined by a map that says, okay, this tank needs to be here. And in that part of Argentina, the land is private. So we needed to go to every owner of the land, say, can we place a tank in your backyard? And you need to give us access to that tank for maintenance. So positioning that thousands of tanks was not easy. And it was not easy because you need to fill the tank with water. So this truck is carrying 12 tons of ultra pure water. And as you can see there, it went into a salt lake and got buried there. And you need to travel to 1,600 tanks to fill the water. Also, Malargüe is a place very well known for the snow. We have a very known ski center, so the snow is frequent. And you cannot stop maintaining a detector of this kind when there is some snow. So the snow is part of the maintenance of the detector. And also the last picture, the wind. Here you see a colleague showing the hair, the speed of the wind, and the wind is also a very common part of the daily maintenance of the detector. So building and maintaining it is not that easy. So just for reference, 3,000 square kilometers. How big is it? You can see here four cities, and you can see, for example, Bogota here would fit 9 times inside the full array of the observatory, London 2 times, and so on. So you can make a quick math, finding out the surface of your city, of your town, and seeing how many times it fits inside the detector of the object. And of course, that effort wouldn't be possible without a collaboration. And I want to remark that word because there are not only 17 countries, the 8 institutions, the scientists. It's a collaboration between them because every country provides the specialities, the know-how, and it couldn't be done without all of those countries collaborating into a single effort to make this experiment, this observatory possible. So you can see in the left picture a very diverse collaboration, meeting in Malargüe, Mendoza, twice a year for sharing the last discoveries and to meet once a year. So this is a more detailed part. I will tell you about the detectors. The first detector, the detector that was first thought to be the surface detector is that tank. That tank is filled with 12,000 liters of ultra pure water, and it has 3 photomultipliers, are those sensors at the top of the tank, and they detect the Cherenkov light. The Cherenkov light is the light that is produced when a particle gets into a medium where the speed of light is less than the speed the particle was traveling. So when the particle gets inside the tank, it produces that cone of Cherenkov light that it can be detected by those photomultipliers. They are in the middle of nowhere, so they need to have a power supply, batteries, solar panels, and a GPS for position and for time. The GPS in the surface detector is mostly used for a very precise timing of the moment of the signal when it arrived to the surface detector, and we can see later why it's so important. And the other main detector of the Auger Observatory are the fluorescence detectors. They are located in 4 buildings, one on the north, south, east, and west, and each building has 6 telescopes. And if you look into the telescope, so inside we have a window here on the left with some lenses for optical corrections. We see a mirror on the left, on the right, that is 3.2 meters high. And in the middle we have the sensor, the camera, that is composed by 440 little light sensors that can see this very low amount of light that is left in the atmosphere when the extended air shower is produced. These detectors has a very low duty cycle. The surface detectors works 24/7. They don't care if it's raining, snowing, windy. They just work 100% of the time. But the fluorescence detectors, they need to have clear nights. The moon must be below the line of the horizon, and it cannot be raining or windy. So they are very useful, very precise for detecting, but they work only 50% of the time. Here you can see a picture in the field with both the surface detector on the bottom right and the fluorescence detector on the top left. This is one of the detectors located at Los Leones mountain in the south. And what is nice about the observatory is that it has this hybrid detection method. So when we are in a clear night, the weather is okay, we can see this shower with both detectors. We can see the shower development on the atmosphere with the signals, and we can see the path that the shower left in the ground. So we are very happy when a hybrid event occurs, because they are not so frequent, but when they occur, they gave us a lot of information about the origin, the energy, and so on of this event. So here are three brief plots about how do we convert the signals to the physics. Here on the top right, you can see the point, each point is a surface detector. You can see the coloring with the clear colors being the first detectors reached by the shower, and the red dots is the far away in time hit by the shower. Here you can see the signal left inside the tank. And with only the surface detector, we can, with the timing of these detections, we can see the shower direction. And the fluorescence detector, you can see here the 440 pixels of each camera, and we can see the trace that the shower left in the atmosphere, and the signal of each pixel. With that light profile, we can see the energy of the particle, because the atmosphere works as a calorimeter. We can translate that amount of light into energy. And we can see with this plot the deposit profile of the shower, the X-max. The X-max is a property of a cosmic ray that tells us which depth of the shower the shower left the most amount of energy. And that is proportional to the kind of particle that generated the cosmic ray. So if we have a proton, say, the proton leaves a shower that develops very near the surface of the Earth, so the X-max is high. If we are hit by, let's say, an iron nuclei, the shower leaves the most of the energy on higher altitudes, so the X-max is an indicator of what kind of particle originated that shower. So I told you before the oh my god particle that was detected by the Fleiss-Stein experiment. This is the highest energy ever detected by the Pierre Auger Observatory. As you can see, it has almost half of the energy of the oh my god particle, and was detected by, let's see here, but 34 surface detectors. And it was on 4 p.m., so the fluorescence detectors were not operating, but we can calibrate the surface detector with the data taken by the fluorescence detector, so we can work even though the fluorescence detector is not operational. Now, I would like to talk about muons, because muons are a key part of the three questions that I mentioned earlier. The muons were very well described earlier, but I want to only emphasize that the muons have the same electrical charge as the electron, but 200 times the mass of the electron. So they can travel through matter without being interfered. So they travel for hundreds or even thousands of meters of rock, soil, as a difference with the electron. Let's say the electron is lost, leaves all the energy in a very few centimeters of water or soil. And the muon is very interesting because the proportion of muons in a shower tell us the muon content is proportional to the primary mass of the primary particle that reached the atmosphere. So the particle has more muons, it is possible that the particle goes heavier. So that's why the observatory in 2015 started an upgrade of the detectors. So the surface detector that I showed you previously was only that water tank. And from 2015, several other detectors are being placed around the surface detector to improve this muon counting. We have a radio detector, that is the antenna located on top of the detector. This measures the radio waves generated when the cosmic ray goes through the atmosphere, and is particularly useful for very inclined showers. Showers that has an angle 80 degrees with respect of the vertical. We have the underground muon detectors that are placed below the Earth, 2.3 meters below the ground. We have the surface scintillator detectors here on top of the tank, and some other improvements like new electronics and new photomultipliers. This is to answer this question about how many muons are hitting the ground when the shower is produced, and to give us a clear picture of what particle hits the atmosphere. Here you can see these underground muon detectors being deployed. You can see the tank here on the left is covered by the soil. You have 3 detectors, 2.3 meters underground. They are the technician deploying that detectors. When they are finally deployed, the soil is put over the speed, and the detectors, the underground muon detectors, get shielded, so the muons can go through the air, the soil, but the electrons are slowed down. So we are very certain that we are only measuring muons of the shower. How is the underground muon detector inside? They are constructed with 64 scintillator bars. A scintillator bar is a plastic bar that is excited when a muon goes through it. It emits a small amount of light, and that light is collected by an optical fiber, and all those optical fibers are routed here to an optical collector. And here we place a very sensitive electronic to see in which of those bars the muon hits. Just to finish the instrument part, I want to show you what is like the detector in the field, because when you think about placing an instrument in the middle of nowhere, there are some problems that you usually don't consider, like the animals. So the animals are very curious about something new on the region, and they happen to like very much the wires. So if you leave a wire hanging there, they will probably chew it, eat the wire. That, for instance, is just an example of things that you probably don't consider when you are planning to build such a big experiment, and you need to first deploy it, and then you will start to see things that are going wrong, and trying to figure out solutions for those unexpected problems. The vegetation is also not an issue, but you can see there how the vegetation goes back to the place, is part of the detector. And finally, the landscape. This maybe answers why Malawi was chosen for this experiment. Because you can see here, we are on top of a little hill. In that hill, this fluorescence detector is placed. And below, we have a very flat and big surface that allows us to place those 1,600 detectors in a very smooth and flat surface, and that gives us the perfect location for a detector of this size. So, just to point out some scientific results. The composition, so one of the questions was, what are they? With the data collected by the Pierre Auger Observatory during these 20 years of operations, the 10 years that we have left, we have seen that the composition, if we go up in the energy, the composition or the mass of the primary particle goes to the heavy side. So the more energetic, the more heavy it tends to be the primary particle. Another question, where do they come from? This is a question that was partially answered by this publication, where we can see this anisotropy. So they do not come from everywhere the same amount. So they are from some regions happen to be more productive of cosmic ray than the others, and we can see that the Milky Way is outside that hot spot. So we know that these high energy particles are not from our galaxy, but they are from outside our galaxy. And the spectrum, this is just to show you that little part of the first plot of the flux that I showed you that it was very interesting. Here we are zooming only in the highest energy part, from the 10 to the power of 18 to 10 to the power of 20. And you can see that the flux that was decreasing in a very steady way, it has some features. The flux goes up in some range of energies, and then it goes down as expected. This publication tells us that the contribution of that flux is dependent of the mass of the primary. So we have the lighter particles here in red. Then as you increase the atomic number, we can see that the sources are providing to that total amount of flux. The heavier particles are providing more events to the higher energy parts. So the first questions that we pointed out are still open. We know more than we knew 20 years ago, but we don't know yet a concise answer to that question. Acceleration is still unknown. We know that active galactic nuclei can generate these particles, but we are not. We cannot say precisely the sources. The origin, we know that they are from beyond our galaxy, but the source is still a mystery. And we can say which kind of particle they are, but with a certain uncertainty. So, just to finish, I would like to show you how these discoveries, this basic science can be applied to not just a physics experiment, but it can be applied to other use cases. For instance, one of the most known applications is the myography. The myography uses the natural muons that are reaching our Earth. Right now, in this moment, maybe 10 neurons are going through your body per second. So that's the rate of the natural muons that that we have, and they can be used to make like the equivalent of an X-ray. We can see through a volcano, we can see through a pyramid, we can see through civil structures like a bridge or a building, and we can find the difference in density of that object. We can see the flux of the muons. We can place a muon detector behind the object. We can see like a shadow that is proportional to the density of that body. So we can see inside some big things like a pyramid or a volcano. Another cool feature about the observatory is that just by accident it can be used to see these transit luminous events, which are like a line. A line goes from the cloud to the earth, but these luminous events happen above the clouds. We saw that with the fluorescence detector. Here you can see in a very dim way a ring, a red ring, that this is taken by a photograph. But here on top you can see how the fluorescence detector can actually see that that feature that is produced in an electrical storm. And here on the left is a sprite. Sprite is also like a jellyfish shaped light that happens when an electrical storm is developed. So this is like a byproduct of the observatory. The observatory was not designed for this, but is capable of seeing them and compare them with another observatories that are dedicated to this specific task. And the fourth push decreases is also a thing that can be measured with the surface detectors of the Pierre Auger Observatory. The fourth push decrease happens when there are some solar storms, and we can correlate the data of some properly experiments that are dedicated to measure this, and we can see a very nice correlation between the observatory, these decreases, and the signal taken by our surface detector. They correlate, so we can use this data to make a solar meteorological observation, so we can see and track solar storms with a byproduct of the observatory. And finally, this is for the people interested in keeping on analyzing data. You can download our open data, which has a policy of releasing the data. 30% of the data is public for you to go to the web page, download the data sets and all the scripts to analyze and to compare the results with your own studies. And you can do it by yourself, downloading the data, or you can sign for a Auger Masterclass. The Auger Masterclass is the same analysis, but is focused on schools with expert of the observatory guiding you through all the process of how it's like to start with the data set to finally have the plot of the possible origins of the cosmic rays. So, many thanks. Any question?
Hello. So first, thank you for the lecture. And second, you mentioned that the detection counts were different depending on where you look. So the term was anisotropy. Is it the same for lower and higher energy, for lower and higher energy cosmic rays, or is it different?
Well, the anisotropy is what I showed you in the plot is with a cut in the highest energies. So when we go to the lowest energy, the sources are different. So let's say the very low energies, we have sources that are in our galaxy, the sun, and so on. We are interested in that cut, the ultra high energy cosmic rays, to produce that anisotropy plot and to show that those very energetic particles are coming from that specific regions. I don't know if that's the answer.
Yeah, thank you. And I have a follow-up question that was, have you been able to detect like periodic events that might suggest some specific source, or yeah, basically?
No, like some event that happens every fixed time is not has not happened, at least as far as I know. They seem to be very random events, not a timed event that happens every second year or more.
Okay, thank you.
First of all, thank you for the lecture. It was really interesting. And you mentioned that dipole anisotropy. Is there any known cause of this?
The cause of the anisotropy?
Yes.
Well, the sources, the location of the sources. Well, you can find active galactic nuclei or supernovas or some specific candidates for the production of these high energetic cosmic rays that are located in that red region. So this is mainly what causes the flux to be more from this part than from that part. But with the data and with the systematic and statistical errors, we cannot conclude that they are coming from a specific source.
Yeah, but why are those sources located at just some certain area of the sky?
I'm sorry, but I cannot answer that. It's outside my knowledge.
Okay, thank you.
First of all, thanks. This is an amazing lecture. And my question is, first of all, I would like to introduce myself. I am Abdullah Shidi from the Kuwait team. My question is, what are the shortcomings for engineers when facing science-based what are the shortcomings for engineers when facing a science-based dominated research field? And what are the shortcomings or situations that come by forcing you to need some outside knowledge from other majors such as physics, chemistry, or even biology? And what can you do to overcome them by yourself?
Sorry, I could not get to.
My question is, in summary, what are the situations, like in a research or in a project, that require you to get some outside help or assurances from other majors, and how do you overcome them by yourself?
Okay, I understood correctly. We are in contact with many other scientific projects, like the Pierre Auger Observatory. For example, the telescope array is a similar detector that is measuring essentially the same but located in the northern hemisphere. We saw that the results were not quite the same, so both institutions decided to make a memorandum of agreement to place some of the Auger detectors into the telescope array facility, so we can mix the data and we can, between the two projects that are looking to different parts of the galactic sky but measure the same, we can correlate data and reach to a unified explanation. So we are not going in our way, but we are trying to collaborate with other scientific projects to reach a common goal.
So what you're saying is that even when facing different based majors such as physics or even chemistry, there is no limits when engaging with other details inside the project.
We have a lot of, there are not only physicists working on the project. Of course, there's a full branch of specialities that are needed for such a big experiment to be successful. And we are this with the meteorological experts, and we measure also for instance, the atmospheric pollution, or how the air is polluted, and this is an indicator of how the fluorescence light is attenuated in the way to the telescope. So the branches and the collaborations are, as long as your imagination can join two different ways of doing science, they can be joined for a common goal.
That was my question, and thanks for the amazing lecture.
Nicolás, gracias. Una pregunta solo. Oh, sorry, I'm going to switch to English. Thank you for the lecture. Just this is a question just out of curiosity. You mentioned that you make available 30% of the data. Is that, did I hear correctly? 30% of the data, yeah? And
Yes, it's not the latest data, but it's a selection of the data with quality cuts, so you don't need to discard much of the events recorded. So the data goes through a process of, let's say, cleaning the bad data and keeping all the good and useful data. And we made a cut, I don't remember now how old the data needs to be released. So probably you have the data from 5 years ago and the origins of the soil.
just wanted to understand whether there was something hidden or not, just simply a selection of the data that makes sense. That's all.
Yes, the quality cut is done previously, and then when you run the scripts, you see the most useful things.
Thank you.
Alright, so there's nothing like the work on the actual field and getting to know even deeper our planet and our universe. So thank you all of the 3 opponents that we have today. It is really a privilege to have you here. students, we know that the international collaboration is beginning actually today for most of you. And well, we should have a great rest